Good afternoon, everybody. So nice to see so many participants around. Welcome to the 2024 edition of the FuseNet Teacher Day. Welcome to the new participants, and also welcome back to the participants from the previous edition. So I think we're going to start with the agenda, and then I see we have Rodivan here with us. Rodi, are you able to unmute your microphone and everything as a panelist?
Yeah, hi Dario, and hello everyone. Dario, I'm able to speak and I think you can hear me, but my video, it says.
Yes. Give me 1 second, I will solve that.
Thank you.
Thank you. Well, Roy, welcome. Thank you for joining us. And I think that you are the first speaker of the day. So I will just, since we already reached a number of participants, I'll give the word to you, please.
Dario, thank you. I mean, it's my absolute pleasure to be here and to open, as you say, the 2024 edition of the FuseNet Teacher Day. My name is Rodivan, as hopefully you can see on the little Zoom thing. I am an academic at the University of York in the UK. So I'm a professor here, and I've been working in fusion for about 25 years. So I've been a tokamak scientist for the whole of my professional life. And it's my privilege and pleasure to currently be serving as chair of the board of governors of FuseNet, so of which Dario and Miro and some of the other colleagues are the engine room, if you like. So I'm just going to say 1 or 2 words about FuseNet and about the Teacher Day, and then I'm going to hand over to the real business, because you don't want to spend too much time listening to me. So what is FuseNet? FuseNet is the European Fusion Education Network, and we have quite a lofty or ambitious goal, which is that everyone across Europe can access the fusion training which is appropriate or good for their role in society. And so this means everyone from kids who are in primary school through children and young adults in secondary school, at university, master students, PhD students, professionals, particularly early career professionals in fusion, also the general public, and people who are more senior in their careers. We want everyone to be able to engage with fusion. And of course, you as school teachers are absolutely crucial in this mission, because you see across Europe many thousands of students. I dare say each of you probably sees hundreds of students each week. So it's how should I put it? You have the future of the next generation in your hands, and it's our privilege to work with you. FuseNet stretches across Europe, and I'm delighted to report that even though there is Brexit, we work with the UK as well, of course, as you will have guessed. So we work across Europe, and indeed in some of our activities we're even able to welcome scientists from outside Europe to come and work with us. But we work across the whole of Europe. We have a number of members who are a mixture of universities. These are member institutions across the whole of Europe, and these include universities, private companies, government labs, and the number of private companies, I should say, as you might be aware, is growing really quite quickly and in quite an exciting way at the moment. So fusion is very definitely moving from a purely publicly funded academic idea to something which is becoming commercial reality. Fusion, I would argue, offers some unique possibilities in terms of a renewable, sustainable energy source. That doesn't mean that we shouldn't be pursuing lots of other ways of providing sustainable, renewable energy, but arguably fusion has some unique advantages. Fusion is really difficult because it's about bringing together 2 small nuclei that are positively charged, don't want to be close to each other, which means that we have to get the fuel extremely hot to do that, and we have to do so in a containment vessel which can withstand enormous heat loads. So heat loads which are in a tokamak, heat loads which are comparable to or perhaps exceed the heat loading on the space shuttle, but not for a few minutes, but for hours or even years. So fusion is really difficult technically, but perhaps the greatest challenge that we have is that we have a massive deficit of suitably trained people. So It's our pleasure to work with you today. FuseNet hopefully can help you in working with our young people and educating them with Fusion. So we are delighted to tell you about that. And one of the next things on the agenda will be talking to you about some classroom materials that we are developing already. We have other material that's available on the FuseNet website, so please do look at that. The final thing I think I want to leave you with is please don't let today be the end of your relationship with FuseNet. So Dario and Mira and the rest of the team, and myself for that matter, are here, and we are delighted for you to contact us and say, it would be super helpful if you were to do this, or is there an opportunity to do this, or can you put me in touch with my local Fusion University or Fusion National Lab? Please do get in touch with us. I'm delighted that you're here today, but please don't let today be the end of your relationship with Fusion or with FuseNet. Dario, I'm not sure if that's what you were kind of anticipating, I might say, but anyway, it's so exciting. We've got teachers, we've got so many teachers with us today, and I hope you all have a great day.
Thank you very much, Roddy. Yes, indeed, I was.
You're muted again, Dario.
Sorry, yes.
Yeah.
Sorry, I was anticipating an intervention like this. Thank you very much. Really energetic for the start of the session, and with a lot of things to think about, especially indeed that we want to keep this relationship with all of you, the teachers, and we want to build something together towards the propagation of Fusion education within your schools and your students. So thank you very much, Roddy, for joining us today. I guess we will move with the next step on the agenda. So that's on me. I will be discussing the classroom materials, and especially the status of the translations of these materials, because for those of you who have been present on our previous events, we have been working, you've seen that we have been working on the translation of the modules. And then I will talk more about it. And those of you who are new to the event, then I will be happy to introduce the FuseNet educational modules for secondary school teaching. Am I in full mode presentation? Yes. Okay, so welcome everybody. And we're going to discuss about our FuseNet educational activities, especially the available materials that we have available for secondary school education. So in this presentation, we will cover an quick overview of the Fusion educational modules. We will discuss on the current status of the translation of these modules into the different languages. And I will show you, for those of you who are not aware of the Fusion educational video that is available on YouTube, I will show you just a small preview. And eventually you will end this presentation having some ready-to-use lessons that you can immediately start thinking to put in your classroom as classroom materials. And yeah, you know all about our Fusion 5 Fusion learning models and the supported material we have. So starting about the modules, these are modules that we have designed in FuseNet for secondary school education. So these are specially tailored material that we hope that you will be able to use during your lessons at school. So they are 5 modules. You can see an overall of more or less the topics that they discuss. Perhaps it's better if I start working on how they were conceived. So as we mentioned, modules, because indeed they cover several topics and they don't have to be used in a sequential way. We wanted to make them as the most useful for you, in the sense that you can arrange your own lessons in the way you see fit. So you don't have to go through all of them, and you don't have to go through them in the fixed order that we present them to you. I think the only fixed module that we have is module number 1, because this is the starting module for all the rest. So in module number 1, we introduce all the concepts, all the basics, and everything you will need to know, or the students will need to know for getting the approach in Fusion and for being able to develop the following modules. But the other 4, you can use in different order. You can see what interests you the most, what interests most of the students, what are the topics that you want to share with the students with more interest than the others. And then you can, after you have used the first module, you have all the freedom to decide how to use the other 4 remaining. So what about these modules? Well, each of these modules consists of the student reader. So it's a manual for the students with all the information. The presentation slides for you, for the teachers to use in the classroom. Then some teacher manual, and then additional exercises. I will go through these materials more in detail, but just to mention that that this is what each module consists of. Where do you find these models? Where these models are already available on our website. So you just go to www.fusenet.eu. You see our site there. You go to our tabs, and you will see in education there is educational materials. You go there, and then the first thing you will find is our educational modules. Why do I say the first thing you will find? Because in this page there are additional materials that you can use, that you can consult. So there is a whole set of educational material available that we have at the FuseNet site, but we are focusing on the modules. So this is why we are having them first. So if you go, you want to see what is in each of them. For example, this is module number 1. So you will see the model information. You will see on the right side the links for you to download all these parts of the module. So the 4 parts I mentioned before, you will have them there. Additionally, if you see on the right-hand side lower part, there is also the translations that we have available for each module. So once you click on one of them, you will have the same set of PDF downloadable for each of the translations. So I urge you to check the website, to check the modules, and see which translations are already available for you to use. Perhaps it's a good thing to mention now that these models are free of use. So there is no charge for using the models. They are free of use. To you, they are licensed under a Creative Commons license, but you can use them and that's done so that you can use the models in the way you want, and you can use parts of it as well for your classroom teaching. But this is a material available online, free to use for you. Okay, so let's go a little bit deeper into the content of the modules and how they look like. So as I mentioned, the student reader is kind of the core of the modules, along with the presentation slides, but let's say this is the text core of the module. It depends, the length depends on the module itself. This is module number 1. Its length is totally 40 pages, and it deals with 5 chapters. So you can see their energy and its role in our world, fusion inside of our own sun, plasma, building a fusion device, and a little bit of further reading. So all of these modules have some additional information that you can consult. So this is what module 1 looks like. So pretty much this is the layout that you will find. Some images, some text, and additional exercises within the module themselves. Now, going to the presentation slides. For module number 1 is a total of 50 slides. And again, I cannot stress enough that you don't have to go through all the slides in order to teach this in class. You are free to use what fits you the most. And that's what we want, because our idea is that we provide most of the material to you, but you are the experts on your classroom on how to teach. We are not expecting to teach you how to teach. That is not our goal. Our goal is to give you a suitable set of materials that you can adapt to your own preferences and to your own way of teaching in your classrooms. So that's why we stress so much in making this modular and easy to use and easy to adapt to the different needs of you in your classrooms. So this is an overview of a preview of the presentation slides. Then we go with the teacher manual. And the teacher manual, the idea behind it is to give you some general overview of the chapter itself. So this contains learning objectives, the topics per chapter, a summary of these topics. We even offer some lesson schemes. So this is suggestions in order to create, for example, a 35-minute lesson or these kind of things that we suggest if you want to start by something. But of course, you can do your class as you want. This is just a suggestion. But then in this suggestion, we tell you more or less what would be good to touch from each of the chapters in the module. And then, of course, there is additional links and a solution to assignments and these kind of things. Yes, so this is another example of what we have there. So the summary and the bullet points of the chapters. Then this is for example, the 15-minute introductory lecture for advanced students. So if the students already know a little bit about Fusion, and then you have introduced the topic before, then this is a suggestion that you could use for a 15-minute lesson, and then the duration, the activity, the materials that from within the module that you can use, and the student activity that we propose. And then in the appendix, of course, there is the solution of the classroom exercises that we provide, and there's the solution with the explanation and a little bit of additional reading and links. So there is more information for you to treat these problems and to share with the students. Then we come to the extra exercises for each chapter. So we rank them in level of difficulty. You can choose which level is most suitable for your students. And yeah, the answers are in the teacher manual, and then you see what works the best if you want to put them for the students to test them and see how they are doing. So this is pretty much the summary of how a full module looks like: the student reader, the teacher's manual, the additional exercises, and the presentation slides. So I will not go through all of them in the sense that all of them have the same components. I'm just gonna mention the topics that each of them deal. So after module number 1, there comes to module number 2, which is Road to Fusion. So this is more a bit on the history of Fusion itself. So the discovery of Fusion, the first devices, the concepts of breakthrough and breakdown, ITER. You will see ITER today a lot in the teacher day. And then, of course, for the reading part that it's common to all the modules. Then the module number 3 is plasma control. So it's more focused on the plasma itself, the introduction to control, how do you heat the plasma, how do you measure the temperature of plasma, then conclusions on this topic and further reading. We go for fusion materials. Also very important as you will see in the presentations today, really important on the success of fusion. So we have extreme materials for extreme settings, the problem of heat exhaust, neutron irradiation and its consequences. Then the concept of a blanket, the breathing blanket of a tokamak or a fusion device is explained, and then the further reading. And then finally, the module number 5 deals with deployment. So this is more on what's after we have achieved fusion. So we achieve fusion, and then we have to put fusion into the energy grid. So this is additional challenges that we have to see. So it talks about fusion power, changing the demand and supply, what can fusion add to the energy mix, and then, of course, the costs at which fusion energy would come to the public, and then if fusion can become cheaper, and how is it that we're gonna reach this fusion energy, so from ITER and onwards, up to the point where we can put energy into the grid. So these are the topics of the 5 modules. They are all of them originally released in English, but I think one of the first feedback we got from you and your colleagues is that the modules are good. We like them, but of course, for us, it's much better to use them in our own language. So we have started already for a while the campaign on having these modules translated into your own languages. So I have to say that we are really grateful to you and the colleagues, because the translation work for these models has been on a voluntary basis, and we have had the help of teachers and researchers all around Europe who have volunteered to help us translating these models. So if you are interested in helping us with the translation, please just send us an email, and we can tell you how it is. And even if this is a voluntary work, then of course we will, from FuseNet, we will happily send you a nice souvenir from us for all your help. And most important is that if you help with a module translation, you will be credited in the translated module. So you will be credited in the translation, and your name will be there for the modules that we release. So this is the status of the model translations up to now. So this is updated for this month. I have to say that we're really happy because we have already translations in multiple languages. Probably those of you who have attended previous events may recall that we started with just a couple of languages that we started as a pilot, and now this has been growing. So again, that's thanks to the support from the volunteers, from teachers like yourself and researchers who have taken this job to their heart and help us with the translations. So you see there the different status. Green is already available on the site for you to download. Blue is processed, still being processed by us, but we have already received the translations. Yellow is that the models have been translated but are still being proofread, because you should know that these models, once we get the translated version, we ask a researcher or a professor from one of our members, who are of course also a local, a native speaker, that they check for the science and seeing that the translation agrees with the part that the English counterpart. So this is the proofread part. And then the orange part is that the model is being translated. So somebody contacted us and say, yeah, I would like to translate this model. And this person has already received from us the set of editable files for translation. So this is the status so far. Our goal is to have everything in green. We're working hard on that. But yeah, we already have some available materials in green on the site. And we are hoping to put some more by the end of the year. We are doing an extra work with all the FuseNet team here to have these models processed, and we are confident that we will speed up these translations, at least for the part that we can process. Yes, and probably some of you from the previous events have seen this, but I would like still to introduce the video that we have. So this is a complementary material for the models. This is a video that FuseNet did for ITER, or with ITER, with a company, filming company, Polar Media from the UK. And the idea of this video was to have a 30-minute video discussing about fusion, introducing fusion to an audience of secondary school level education. So we try to tailor this for secondary school students as an additional material for the models. So I'll see if I can show you a preview. Let me see. I hope the sound is working.
Hydrogen as isotopes are deuterium with 1 proton and 1 neutron, and tritium with 1 proton and 2 neutrons. So they collide with a very high energy and temperature around 150 million degrees, which is 10 times higher temperature than in the center of the sun. And they can fuse. So we have helium element and we have 1 neutron. So this is the most important part of the reaction, because neutron takes 80% of all energy of the fusion reaction.
It turns out we need strong magnetic fields.
So we actually need 2 types of magnetic field. The first one happens in what we call the toroidal direction. This is following the shape of the torus around. But that wouldn't be quite enough to keep it completely confined. So what we do is we actually want a magnetic field as well in what we call the poloidal direction. And that sort of introduces a twist.
Yeah, so this is a preview of the video. Like I said, it's a 30-minute video that you can find in our YouTube channel. Anyway, we will send you an email afterwards with all these links and important information that you can access. But just take into account that this video exists, and we would be really happy if it helps you in teaching fusion in the classrooms.
Hydrogen as isotopes are deuterium.
Yeah. Okay, so I think this is the end of my presentation. So what we've seen today is an overview of the educational modules, a preview of the educational video that we have available. And yeah, I think I will end with, of course, thanking you for joining the Teacher Day and inviting you to join us in our future editions. And yeah, I think this is just the starting point of our day-to-day that we hope that you will enjoy, because we would like you to see what is the different initiatives that we have in Fusion. And most important, we want to bring you virtually into the different Fusion devices. And today, for this day, we have 2 great sites that we are really willing to take you in virtually, and that you see this place. So thank you very much. I will stop my sharing. And with that, I think we will start with one of these tours, one of the very important Fusion research facilities for Fusion in Spain. So the CIEMAT, the Research Center in Madrid. And let me see if I can find the speakers, and then we will grant them privileges.
Hello, welcome.
Nerea and Belit, good to see you.
Here.
Okay.
We're both here sitting. Good afternoon, everybody.
Well, allow me to introduce then Nerea Panadero and Belit Garcinuño. They are researchers from the CIEMAT institution in Madrid. If you would like to tell a little bit more about yourself, we'll be happy to hear you. I think the presentation is better if you do it yourself, but thank you so much for being here. And yeah, now the floor is yours. Thank you so much.
Thanks to you, and thank your organization of FuseNet to organize this particular visit to our facilities. We are very happy to have the opportunity to show you our laboratories. And well, I'm going to share a presentation here with my colleague Nerea that will explain later than me the TJ2, and I cannot see the mouse. Sorry. No.
Yes.
Okay, are you able to see it?
Yes, we can see.
Perfect. Okay, so I will start briefly explaining what is our laboratory. We are the National Fusion Laboratory at CIEMAT, which is in Madrid, in Spain. We are this part of the buildings that compose all the CIEMAT site, which is very big. There are a lot of departments. And here, and particularly in the National Fusion Laboratory, we have 5 divisions working all together in different aspects of the nuclear fusion, both for experimental, operational point of view, also development of technologies and theoretical approaches different. We are all about 150 researchers, and we will show you today part of the experimental activities that we develop here, focusing on the more in plasma components and also the out of vessel part related to the green blanket components and liquid metal technologies associated with it. And I will skip to the part concerning my research, and I will show you the part of the liquid metal laboratory here in CIEMAT. We are part of the nuclear technologies division, working mostly focused on the green blanket technologies. I will explain a bit what is the green blanket, because I don't know if you are aware of the issues or the points that we have related to the liquid metal. After the deuterium-tritium reaction, the neutrons that exit the vacuum vessel will collide to a component in order to recover the energy of the neutron that carries the 80% of energy that we have seen in the video. And we have to recover that heat to translate into electricity. And then we have to produce tritium in order to have a closed cycle in self-sufficiency of the tokamak, or the reactor, the fusion reactor. And so in some components of blankets, we use a liquid metal in order to produce the tritium and also to recover the energy. And this has a lot of issues or showstoppers that need to be overcome to comply with the fusion reactor as a true source of energy. And also related to the neutrons interaction with materials, there is a lot of uncertainties on how these materials will behave under the neutrons irradiation. And from the structural point of view, the operational point of view of the reactor, we need to know how these materials will become as mechanical properties. And for that, there is another facility called Ifmiftones, which is being constructed here in Spain, luckily. So where they will produce a neutron flux to irradiate different materials to test their behavior. So to produce the damage as close as possible, and it will be in a reactor. And how we produce these neutrons with a pure lithium flow of 15 meters per second of a curtain of lithium being irradiated with a deuterium accelerator. So we have other issues related to the operation of pure lithium and also with the lithium that I will introduce in the later slide. So here in the Liquid Metals Laboratory, we group a lot of facilities devoted to overcome these possible issues that we will face during these research activities that we do for the fusion technologies. We focus on instrumentation, chemical analysis of these materials of lead lithium that is used in a reactor, a spring blanket, or pure lithium, to have a very good control of the material, the status, the impurities, and the content of the purity of this material. We also work on tritium extraction to recover the tritium generated in the blanket and also to purification for the purification of the lithium. Safety, because lithium implies several issues related to the reactivity with water, humidity in the air, oxygen, and so on, and also purification and corrosion activities. So I will have this opportunity to show you. Tell me if it is okay. Yes, I think it is. So starting the laboratory, one of the buildings that we have here in Tiemat is this laboratory. We enter here and we have a cutting machine with is devoted to cut lead lithium ingots in different sizes, so we can use them for the different experiments that we have in the laboratory. So we also have different components, glove boxes. This is a view on the other part. We have different glove boxes for the manipulation of these materials, the lead lithium or the lithium, pure lithium, under an inert atmosphere of argon, so we avoid the oxidation and the reaction of these materials exposed to the air. And we use them also to mount different subsystems that we use for the experiments. We have here another glove box devoted to the melting of the lithium. This glove box has a modification because we have a melting tank here in the bottom part, so we can insert in the inlet the lithium ingots to be melted under the inert atmosphere. We can take samples for the analysis, and also when we check it is everything okay, we can transfer this lithium to other facilities that we have in the other part of the laboratory, which is here. Sorry. We have here other experiments, and we transfer the lead lithium to these circuits. As I have mentioned, we also work in the instrumentation. We have here a vacuum test bed. We put some components needed to be tested against leaks under high temperatures. And also we right now are working on the development of electrochemical sensors in order to measure hydrogen isotopes concentration inside the liquid metals, both for lead lithium and for liquid pure lithium, because there are no commercial sensors that being able to be used under these conditions of operation due to the high reactivity of these liquid metals and the operational temperatures. Here we go also on the corrosion of materials. We want to understand and know which materials behave better under the liquid metal flow. So we have this loop called cyclo. Cyclo is an isothermal circuit with forces circulation with an electromagnetic pump. So we can perform experiments at very high velocities and at very high temperatures of operation. And we put samples here inside the flow of the lithium during many hours. Now we are carrying out some experiments at 1,000 hours of operation to test the behavior of these materials. And prior to put the samples in this loop, we have also other systems to test the corrosion of these materials, but without flowing, just in static stagnant conditions, under vacuum and also under a controlled argon atmosphere, which is called COES. Here in our lab, we have also this other loop, which is called Clipper. This circuit is bigger than the other one. It is devoted to develop experiments for the tritium extraction from the liquid metal. As I mentioned, in the breeding blanket, we produce tritium in order to have a self-sufficiency in the reactor. So we need to test systems aimed to extract the tritium from the lead lithium that is being produced. We have this circuit which can operate up to 550 degrees and at high velocities, up to 4 liters per second with the permanent magnet pump that it has. We have here some components mounted because we perform different experimentation here, not just the tritium extraction, but also we can couple other components to test the heat exchange or the lithium with other systems, and how we can inject the deuterium inside the liquid metal to test the further extraction. And finally, we have here another small experiment. They aimed to validate this as a first approach, those technologies needed to be in the lead lithium in static conditions. For example, hydrogen sensors or other coatings and so on. And we will go to the other laboratory that we have here in CIEMAT, which is more focused on the lithium applications, as I mentioned, for the IFMIF Donnes facility. We have here a glove box, and inside the glove box we have LIDAR, which is a lithium experiment to validate the hydrogen trapping system for the lithium. This is how to retain the tritium hydrogen isotopes that will be produced during the operation of the facility. So we have them here as an impurity of the pure lithium, and we need to retain them using better materials, and we test them how they behave. We have this inside a glove box because we don't want to have any issue related to the operation of lithium when it is melted because of its reactivity. And related to this, we have another big facility, which is LIFIRE. LIFIRE is devoted to explore the lithium reactivity under different atmospheric conditions. So we can put lithium inside, heat it up and melt it, and put different atmospheres, argon mixtures of argon with air, and control it, humidity or water. So we can know how it behaves under different conditions, and if we will have or more strict or relaxed limits of the operation with pure lithium. And yeah, last but not least, we have another big facility that we don't have right now the 360 view, but which is LITEC. LITEC is another big facility that is being constructed right now, being installing right now in Granada. It's a pure lithium loop, big loop with almost 700 liters of pure lithium, aimed to validate the whole purification system that will be in Donetsk. So we will have here different trapping systems, and you can see different glove boxes, tanks for containing the whole amount of lithium that we will have, a lot of piping systems to connect all the components, and this is was being finalizing. We have a lot of work to do here, but as soon as we have the complete video, I will show you how it became, so you can use it in FuseNet to be shared with the community. And now I will give the floor to Nerea, so she will explain you the other facility that we have here in Tiamat.
Thank you, Belly. Thank you, everybody. Pleasure to be here. Good afternoon. So yes, I'm Nerea Panadero. I also work in CIEMAT, but in the National Fusion Laboratory, but in the part related to plasma physics. So before we get into this part of extracting heat and so on, we need to hold up a very hot plasma of deuterium and tritium for a long enough time with high enough density, so we can have enough deuterium-tritium fusion reactions, so we can actually produce energy. To do that, different approaches has been tested for several decades all around the world. One of these is the stellarator. You may have heard about them. In these devices, we trap this. Can you see the movie? I'm sorry.
We were, but now
You were,
there
yeah,
we go.
But let me change the quality because it was better for. Oh no, it's fine. Okay, sorry. I'll go on. So yeah, stellarators are a kind of fusion device in which we trap this this very hot plasma with magnets, with coils in which we have a current that generates a magnetic field. In this kind of device, we don't have a current flowing inside the plasma that we have in tokamaks like ITER. So an example of a stellarator will be Palestine 7X. So you may have heard about it. Is the most optimized, the most advanced stellarator now in the world, with the task of proving that is can be as good as a tokamak. And we also have one of these devices in CIEMAT. It's the stellarator GG2. It could be like the older but smaller cousin of Palestine 7X. I'm going to show you now the BC2 TG2. So let me see. Okay, let's start here. As we go inside TG2 hall, it may take a few seconds. Yeah, here we are. So we enter into TG2 hall, which is also in CIEMAT in Madrid, in Spain. You can see this red structure which holds all the TG2 vacuum vessel and all the components. So TG2 has been operated here for some years, since 1997. This is the third device that we have in the National Fusion Laboratory. It's like a medium-sized stellarator. If we look from above, TG2, we see that from here. Maybe this is not the best view, sorry. It's so complicated. From the center of the device, so if you can imagine a donut, from the center of the donut to the center of the plasma, we'll have 1.5 meters. And the donut have like a minor radius, like the dot will be like 22 centimeters. So you can see that TG2 is covered with many things, because the aim of this kind of devices is studying how the plasma behaves under different circumstances, different temperature, different densities. We have different magnetic fields. We have different gauges, shapes of the magnet cage that holds the plasma. So we need to study how this plasma behaves, how the hydrogen moves inside the magnetic field, how particles escape this cage, how lights interact with it. So it's kind of difficult to imagine how TG2 actually is. So I'm going to stop very briefly this virtual visit, and I'm going to show you a model, a 3D model of TG2. So these blue things, these are the coils that trap TG2 plasma, which is shown here in pink. So we have these circular coils following a twisted coil that goes here into the center. Then we have the vacuum vessel in gray with all the windows that allows us to study the plasma. Okay, let's go back to the visit. So we have a device like this. We have a plasma, but how we create the plasma, we need some heating devices. And in TG2, as in many other facilities like this one, we have two kind of heating systems. So the first one will be sorry, I'm trying to find the best view, but it's kind of difficult. Well, this one is a good one. So we have TG2 here, and one of the heating system will be what we call a neutral beam injector. We have inside a Faraday cage, we have an accelerator. So we accelerate hydrogen ions up to the energy that we want. In our case, is 30 keV. Once it is accelerated, we neutralize it, and then we inject it into the plasma, so it can collide with the atoms, with the nuclei inside the plasma, and transfer the momentum and heat them. So in TG2, we have two of this injector. One is here, and the other is in the opposite side of the device. We have a second heating system. So this should be the other injector. The other heating system that we are seeing from above is like a very huge microwave. We have some microwave that instead of heating the water that we have in food, like in a microwave oven at home, what we do is inject a microwave with the same frequency of either the electrons or the ions in the plasma rotate along the magnetic field lines, so they can resonate and accelerate, and you can heat them this way. So you have here these two, what we call gyrotrons, with two injection lines that goes under this floor, heating into mirrors that guide them to the plasma. Like for instance, you can see here, the last of here, the microwave will hit this mirror and go inside the plasma through a window. So as I said, the goal of this kind of facilities is to study the plasma, and we have many different diagnostics. We have what we call passive diagnostic that only collect the light or the particles that escape the plasma. Also, we have active diagnostics. So we inject particles or we inject light like lasers and see how they interact with the plasma. I'm going to show you a couple of them. Like for instance, go back here. We have what we call a heavy ion beam proof. We have heavy ions, in this case it's cesium, and we accelerate them. The beam will go through this tube here and will be accelerated. Each of these kind of rings will accelerate the cesium beam up to 200 kiloelectron volts. They will go into the plasma, they will interact with it. So this beam will change the energy, the direction. And once they have go through the plasma. We will collect them and in this part here, and we'll analyze. And with this, we can calculate the potential of the plasma, the density fluctuation, and very different things. Another important diagnostic, let me check, will be what we have here in this big structure. This is Thomson scattering diagnostics. It's one of the most important because it gives us the density and the temperature of the plasma at a given time for the whole plasma radius. So we have a laser that is injected into the plasma. The electrons interact with the light of the laser, and through the scattering of this electron, we can calculate the density and the temperature. Now I want to show you, because it's the TG2 control room. So everything you have seen inside the hall has been, it's controlled from this control room. The only danger is that we have a high voltage, there's nothing else. But anyway, we control this from here. I'm going to guide through what a typical experiment in TG2 will be. So here we have the control engineers that will decide when the current that goes through the coils will start increasing. When the values reach a certain value, we will inject a controlled quantity of hydrogen. We usually work with hydrogen, not with deuterium tritium. So the people sit here, which are the operators, will control the amount of gas that we put. Then people sitting in another control room will start the heating system. So this gas of hydrogen will start becoming a ionized gas, which will be a plasma. This will last a very short time. So we only have 300 millisecond plasma, 200, 300. That's very far from what a reactor needs. Also, our densities are very low, like the temperatures too. We only reach 20 million degrees, but it still is very far from what a reactor needs. So once we have this ionized gas, the plasma, we will start all the diagnostics. We will collect all the data, and we will visualize it from the control room. And decide if the experiment has gone well or not, or we need to repeat it. Maybe. So this will be the inside part of TG2. Well, from here, you can have a better idea of the size. So this is, like I said, from here to here, more or less, would be 1.5 meters. And I think that could be all.
Okay. Nerea, Belit, thank you very much for this amazing presentation. I think it's really good to see what the actual research centers are doing in fusion and be able to grasp virtually what this is, especially because I would say that there is sometimes the misconception that fusion is this person in their backyard doing weird stuff, and this is this is more national laboratories and big projects in fusion. This is the way we're pushing fusion forward. So thank you for showing this. I will open the floor for questions. I haven't discussed how we're gonna do it. So there is a Q&A panel down in your Zoom connection. So you feel free to write the questions there. Also, if you feel like you want to have a question by voice, then just raise your hand and we'll find you and unmute your mic. While the teachers do that, I would like to start with a question for the two of you, because I know that you are also active in CIEMAT's outreach initiatives. I saw that these, for example, the tours are Divulga CIEMAT, which is an outreach initiative in CIEMAT. And we have here teachers from all over Europe. So if a teacher is interested in having their students visiting these kind of facilities, I would say it's easier for the teachers in Spain or in Madrid, but still, is it possible for teachers to collaborate with you in a sense that if they want to show the students something about what is been doing in CIEMAT, this kind of research, very important for Fusion, if you tell us a little bit more what you can do and if there is the possibility to do even something for the teachers that are not easily getting close to Madrid for this.
Well, actually, during this summer, last summer, CIEMAT, Divulga CIEMAT is now a new section of CIEMAT. It's part of Med Night, European Med Night. So they organized a visit of teacher, like a summer school for teachers. I don't know if at Europe scale or just national, but they hosted some teachers during 1 week, so they can come here and go to the different departments and so what we do here in CIEMAT. So there is a website linked to CIEMAT's main page, I think, which is divulgaciemat.es, maybe. And here everybody can find a lot of information about the activities devoted also for teachers, for students, and so on, because we also perform a lot of talks in schools, universities, and high schools. So yeah, I don't know if out of Spain there is a lot of activity, but it's just a start point, I think.
That's a good point. Yeah, thank you. That's really good. I think with the for the attendees, we will share these links with you because it's important. Also, if I understand correctly, we can also share the 360 view that you just showed us, right? So we can share with the attendees. So if you find it useful, maybe to display them in your classrooms, but also this the initiative of Divulga CIEMAT, we'll be really happy to share with the teachers. So I think it's good that we have this connection between labs and educational sites.
Beside that, we have like every Friday a person visit to DG2, but that opens in September and the slots goes like the same day. So it's quite difficult to get a spot. But we also have open days during the science week and some kind of thing. Maybe that might be interesting.
Okay, thank you very much. I don't see questions for the moment. So anyway, if you the attendees have any questions that you come up with later, then you can tell it to us, and then we email to Nerea and Belit. Thank you very much again. That has been a really nice tour of Madrid. Appreciated that so much. Wish you lots of success in your current research and future endeavors.
Thank you so much.
Thank you so much for participating in our event. And with this, yeah, thank you. And with this, I think we can move to the coffee break. So the coffee break will be until 15:15. After the coffee break, we will have a presentation from DG Ener. So that's the branch of the European Commission that deals with ITER and ITER contractors. And I suggest that you are here in time because as a little preview of what we're going to hear, there is initiatives funded by the European Commission for teachers to go to ITER and visit the ITER site. So we will be hearing that after the coffee break. So see you in 15 minutes, and thank you very much.
Hello, Dario.
Hello, Clotilde. Welcome to the event, and hello, everybody. Welcome back from your coffee break. So I see, yes, most of the people is back. That's really good. I made a really good promotion for you, Clotilde, before the the coffee break, that you would tell us interesting things about the Commission is doing with the teachers at ITER. So I think it works.
Thanks a lot, Dario. So now I feel the pressure.
No, I feel the pressure. I think you have really nice things to tell. So
okay,
it will be really
so
good. Yes, so officially welcome to the event. This is Clotilde Catnaneo from DG Energy from the European Commission. And she will tell us a little bit more of the involvement of the European Commission with ITER and with the teachers themselves. So Clotilde, welcome, and please go ahead.
Thank you very much, Dario. So I will first try to share my presentation that I will use to present the initiative. Can you tell me if you see my full screen?
Yes, we see full screen.
Okay, very good. Thanks a lot. So again, thanks a lot, FuseNet, for the organization of today's event and for the invitation. So as Dario said, my name is Clotilde Cattaneo. I work at the European Commission in the ITER unit, which is behind the organization of this EU Teachers Visits to ITER initiative. So just give you a brief introduction on how I plan to structure the half an hour I have to present the initiative. So first of all, I will give a very brief overview on why the European Union is supporting fusion and on how it is supporting fusion. And then we can get to the core of the topic with how we promote fusion education through the EU Teachers Visits to ITER. And we will also talk about a potential 2025 edition, as well as the application procedure and selection. So first of all, why is the EU supporting fusion? So we know that fusion can provide a safe, cost-efficient, and sustainable solution to European and global energy needs of the future. And it can be part of a clean energy mix that can complement renewables and other energy sources. So as you may already be aware, by 2050, Europe aims to become the world's first neutral continent. So fusion energy could play an important role to meet this target beyond 2050. Then the EU is also supporting fusion in order to maintain science excellence and to nurture the industrial and research know-how, and as well to benefits from the investment that is being done in terms of economic growth and employment in the EU. Because manufacturing, for example, the European share of components for the ITER projects or providing infrastructure means that the European industry is working with suppliers from all over the world. So it's becoming more competitive and is also entering in new business markets. So we have already also some figures on the key investment of ITER, of the EU in ITER. So specifically, ITER has produced, created between 2009 and 2017 over 40,000 annual jobs. And it is projected to create 83,000 more until 2030. There are many operational contracts, specifically 529, that were signed with EU companies for the construction of the ITER project between 2014 and 2022. And then the benefits for the EU economy, because the significant investment is directly reinjected in the economy with over 6 billion euros paid to EU companies between 2014 and 2022. As well, even if fusion energy is still at a research stage, it's not yet a reality. There are innovations stemming from major fusion projects like ITER that are leading to technological advancement in other industries. So, like two key examples. The superconducting magnets that are being researched and perfected to control fusion reaction are also used for the magnetic resonance imaging, which are indispensable tools for doctors. And another example is in material sciences. So the cockpit shapes in the aeronautics industries are realized thanks to a pressing metal technique that was originally developed for the ITER project. And then if you are interested already to know more about other let's call it technological spin-offs or success stories, there is a new website that has been developed by Fusion for Energy and Eurofusion that puts together a collection of these success stories. So I will try now to open it, and you can see it here. You have different examples of different technologies and you can browse into the different articles. You can find it by simply Googling European Fusion Technology Marketplace. Now, let me, okay. Then just to quickly also introduce how the EU is supporting fusion. So the European Union is contributing already to 45% of the ITER projects through both cash contribution, but especially by providing half of the components. So these components are specifically procured and manufactured with the Fusion for Energy, which is the EU organization based in Barcelona that is working together with industry and research organization to actually produce all the components that are then shipped and delivered to ITER. And just to give you an idea of the amount for the financial period 2021 to 2027, the EU allocated 5.61 billion to the project. Then the European Commission is also working to support the project itself. So DG Energy specifically is representing Europe in the governing body of the ITER organization, which is the ITER Council. Which is responsible for the promotion and overall direction of the whole organization. It comprises representatives of the 7 members that you also see listed in the pie chart, and is supported by technical advisory bodies. The GRTD, which stands for Research and Innovation, coordinates instead the funding for fusion research in Europe through the Euratom Research and Training Program. And then we have, of course, the already mentioned Fusion for Energy. But now we can get into the core of the presentation. So on how the EU is promoting fusion education through the teachers' visits to ITER. And I will try now to play the video. So it's very short. Probably the quality of the image will not be there, but I hope you can at least follow with the audio and the subtitles.
Welcome to the heart of cutting-edge science and innovation in the European Union. Last year, the European Commission organised a series of educational visits to the ITER facility in France, bringing together 100 teachers from schools across the EU. These educators embarked on a unique tour of the facility, delving into the world of nuclear fusion. Their aim? To equip them with the knowledge and resources they need to help ignite the curiosity of their students. With its goal of producing energy through a fusion reaction similar to that of the Sun, ITER is a project that fires the imagination. A collaborative effort encompassing members representing 3 continents, over 40 languages, half of the world's population, and 85% of the global gross domestic product. It bears testimony to the EU's commitment to shaping a cleaner and more sustainable future. The impact of the teachers' visit did not stop at the ITER facility gates. Armed with their newfound knowledge, the teachers returned to their classrooms to spark flames of curiosity in thousands of students across Europe. In this way, they are helping to nurture the next generation of Europe's scientists and engineers. The students' enthusiasm is palpable as they connect the dots between fusion energy and global issues that they care about, such as the environment and climate change. The students learn about the relevance of fusion in addressing modern energy problems and understand its potential role in shaping our global future. The impact of the visits continues to grow. Over 3,500 students have been engaged, and the numbers are rising every day. But it doesn't end there. These dedicated teachers are not only transforming their own classrooms, they're becoming ambassadors, sharing ITER lessons and materials with their peers across Europe. Fusion science is not just a field of study and a career opportunity, it's a call to action. Developing and maintaining fusion skills strongly benefits our society. As young Europeans immerse themselves in this exciting journey, they will play a pivotal role in shaping the EU's success on the global stage. For more information about ITER and fusion energy in Europe, please visit the website.
Okay, so Yes, I hope you could follow a bit. So this video was produced this year to illustrate the visits. So it was actually filmed during one of the visits that took place during the spring. It's not available online yet, so you really have a preview of this video. But now I just wanted to explain a bit how the visits are organized, how they are rolled out. So we had so far 5 visits. 3 were organized in 2023 over the summer, and for a total of 100 participants. And then there were 2 other visits organized in the 2024 edition in March, with 61 teachers participating. So the actual day at ITER is structured as a full day program, which we arrive at the ITER site, and then we have in-depth presentation of the ITER project, which is given by the ITER organization. This is followed by a site tour, giving participants like a very first-hand look at the ongoing work and the technologies in development. This work site tour differs from one visit to another because this is a work site. So depending on the actual work that is ongoing, some parts could be not available or not accessible on the day of the visit. But typically, teachers are able to visit the assembly hall, and that's where the components arrive and are put together before being transferred to the tokamak pit. In 2023, Europe was still manufacturing at the ITER site the big poloidal field coils. So teachers in 2023 were also able to visit this facility where they were producing these magnets. So yes, after the worksite tour, there is a well-deserved lunch break. And then the afternoon session shifts the focus towards the broader educational efforts. So it is led by the European Commission, and it comprises a presentation on the EU efforts in fusion. So something similar to what I was explaining before, but of course more comprehensive and developed. Then we have a very useful presentation on FuseNet teaching materials available. And then there is a practical workshop where teachers have the opportunity to brainstorm and start formulating ideas on how to transfer the knowledge they acquired on ITER and Fusion to their students. And the visits normally ends around 4:30. So you can see here is a picture with the work site in the background of one of the groups that visited ITER last year. And here we have more pictures. On the left, you have your colleagues presenting the ideas that they have brainstormed during the practical workshops. In the center and on the right side, these are pictures taken from the assembly hall during the worksite tour. But of course, I mean, the visit is not just about going to ITER. The networking part is also very important. So typically each group arrives the day before the scheduled visit to ITER, and they participate in a networking dinner during which teachers start meeting and knowing each other in an informal setting. And this is important to foster a sense of collaboration among participants before the formal activities start the day after. So on the left, this is one of the first dinners for the visits that were organized over the summer. So in that case, participants were very lucky because they could have the dinner in a nice garden in Aix-en-Provence. And on the right side is a picture of teachers who on the second day spontaneously gathered together to continue and indeed this collaboration and these exchanges, because we basically organized the networking dinner and the day at ITER, but then basically all participants, they traveled the day after the visit for a logistic reason. But we don't organize a second networking event. But in any case, we witnessed that participants spontaneously gathered together. I think it's important to highlight that this is quite a unique opportunity because it's a very diverse group of teachers coming together. They come from all over Europe. So it's different countries, different school system coming together, but probably sharing the same challenges and the same objectives. So it's really a quite particular opportunity to discuss with your peers on common topics and start exchanging ideas and good practices in how you can teach fusion or related topics to your student. So the learning doesn't actually end with the visit because upon returning to your school, teachers are requested to organize follow-up activities to translate their experience at ITER into meaningful lessons for the students. So we don't provide any specific format. We give freedom to teachers to organize the activity as they wish, as they please. We do provide a fact sheet that we have produced to facilitate the task. So this fact sheet is actually putting together useful materials that teachers can use to prepare their class and their activities so that they don't have to actually start from scratch. And finally, we ask you to report on the activities you have organized at school. So we gather qualitative and quantitative feedback and data, both on the visits itself and on the follow-up activities. And we do this through a simple online service. The information is then compiled to produce a final report on the impact of the visits. So we learn about the impact, but also we learn about what worked well, what didn't work so well, so that we can also improve the format and do something that is useful for you and your students. Here are some examples of activities that were organized by teachers following their experience at ITER. So as you can see, it's very different formats. So we range from multimedia presentation to educational escape rooms themed around fusion energy and ITER, role play exercises to demonstrate fusion processes. Some teachers organize group projects on fusion, ITER and environmental implication, because what it's interesting to note is that we can present ITER or fusion to students from a purely scientific or physics point of view, but it can also be presented from indeed environmental or climate change implication, from a historical or international relation perspective. So it's quite polyvalent subject. Other teachers simply shared their personal experience and photo from the visits. Others organized the construction of a reactor tokamak model with Lego bricks. They organized interactive debates about fusion and fission, the advantages, disadvantages, etc. One teacher even managed to develop a mobility initiative using Erasmus Plus funding, and he will be able to bring from Germany his students to visit the ITER site in March next year. So we see that indeed there are many interesting and useful initiatives stemming from these visits. Then talking briefly about the impact and outreach. So far, we had 161 teachers participating in 5 visits. 2,070 students took part in follow-up activities according to the report in 2023. Almost other 2,000 took part in activities according to report to 2024. It is to be noted that the number of students reached was at the time of the reporting. So the numbers have likely increased since then, especially because some teachers reported that they are likely to repeat the activities in the following years. So we have to bear in mind that one teacher, of course, reaches many students, and actually the ultimate aim of the initiative is to raise awareness about the ITER project and fusion in general among young Europeans, so that we can inspire students to consider fusion as a possible study and career option. Because we have to consider the fusion is a long-term endeavor, and that we will need a future skill generation of scientists, engineers, researchers, project managers to be able to research, construct, and ultimately operate the fusion power plants in the future. So now is the time to think about a possible 2025 edition. So today I'm not able yet to confirm when this will take place, because of course it's an initiative that takes time to organize. We still need to go through many administrative procedure and organizational aspects before we are able to confirm some possible dates for the next year. But in any case, we hope that indeed we will be able to organize them, and we hope to see a lot of application, so that maybe next year you will be one of the teacher in this picture. And specifically, there are some application and selection criteria that we apply. So indeed, in order to participate, you will need to fill in an application form. So typically, we send around a few months in advance before the visits take place. We send around an invitation with an application form. The invitation is disseminated through European and national teachers networks, through FuseNet. So if today you are attending this event, you are likely to receive the invitation in the future months. And yes, we have application form because we need to do some selection. Just to give you an example, last year we had 60 places, but almost 300 applications. So we apply some criteria. First of all, a geographical balance, because we aim to have teachers from all over Europe and a very diverse group. So there are some places assigned to different EU member states. So the bigger the member state, the more places are available. So typically, teachers coming from Germany are allowed to have 5 to 6 places, whereas a smaller country like Malta or Luxembourg is 1 to 2. It also depends on the number of applications we receive. So, but we need to keep this balance anyway. We also keep a gender balance, but that works out really well because also the application we receive are already well balanced. Then we do a selection also based on the subject you teach. So it's primarily STEM teachers, but also social science teachers. We also select on the base of English knowledge. So we don't test your English knowledge, of course, but the visits take place in English. So in order to participate, you need to be able to understand English and to communicate. And then, of course, availability to visit ITER on the date proposed, because they are a fixed date that we cannot move. So we are trying also to select dates that are convenient to as many member states as possible, taking into consideration the different holidays all over Europe. And then the motivation. So there is a short motivation to fill in that, allow us to understand the interest of the candidate to participate in the visits. So stay tuned. We hope to be able to send you more information about the 2025 edition in the next months. And yeah, we hope to have as many of you applying for participating next year. So thanks a lot. If you have any question, I will try to reply to them. So just please let me know.
Thank you, Clotilde, for this presentation. So yes, you do have questions. So let me. We have in the Q&A session. I will read to you. So there is Tiago asking, where will be the video available, because he was featured there. So he would like to see it again, and I think we all do. It's a really nice video. So congratulations, I would say. So when and where will it be available?
So indeed, the video, unfortunately, is not online yet. It was developed over the summer, so we didn't publish it yet, because we want to do it in relation to the launch of the third edition. But of course, as soon as it will become available, we will start disseminating it widely. So I hope as well FuseNet can help us spread the video, but it will be done likely before the end of the year will become available. So Tiago, I hope you will be able to watch it again.
Okay, yeah, for sure. You know that FuseNet, like you mentioned, we will, of course, disseminate all your initiatives, so especially the video and also the application for the visit in 2025 when it comes. And then that leads me to the second question. So it's very, very pointedly like, I would like to register for the visit in 2025, says Stefan. How can I register? So
So thanks for the interest. First of all, it's good to see that people are interested in the initiative. So basically, as I said, we didn't develop a website just for resource-related reason. But what we did in the past was to disseminate the invitation through national European networks, like FuseNet, for example, that would then disseminate the invitation through their stakeholders list. So for you, for example, you would receive it for sure from FuseNet and probably from other sources. Depending on the resources available, we may be able to do a website where all the information will be hosted, but otherwise you would receive this by email.
okay, thank you very much, Clotilde. And yes, to the attendees who are interested, because it's not only Stefan, but it's also Simon with a similar question. So to all of you who are interested in joining the initiative, as soon as we receive information from Clotilde and DG about the way of applying for the 2025 visits, we will send it to the list of attendees to this event. So that's why we have your emails, and then all of you will receive the message indicating the link or the webpage or the way the commission finds for the application to this event. You will find it through us, for sure. Okay, I think that's most of the questions that people have. There is one last question from Tiago that says, how do we submit more follow-up activities? So that's a good I think he participated in the previous year, so he has already done so.
Okay, yeah, true. The follow-up activities were collected by our contractor. So if you, in the meantime, did more, you can, it was through an online service. So you can still use the functional mailbox that we use for communication during the preparation of the visit. So it was, I think, ITER visits, GOPA, something like that. I don't know if you still have it. Otherwise, I will send it to Dario and then he can forward it to you.
Yes, definitely. We will do that as well. Well, I think there are no more questions. Clotilde, thank you very much for joining our event. We're really happy to collaborate with you and DGNR in this great initiative. My fingers are crossed for having the visits in 2025 and the dates. So also congratulations from our side on this great initiative. And yeah, thank you for being here with us.
Thank you very much, and have a good ITER tour now with Kirsten.
Yes, we will. We will. Thank you, Clotilde.
Thank you. Bye-bye.
Bye. Okay, so after the discussion about the visits to teachers to ITER, I guess it's time to show the star of the whole visit and event. So it is time in the agenda for us to go through the ITER tour, and we are really happy today to have Kirsten Haupt from the communications office at ITER and longtime friend of FuseNet to be part of this event, and she will lead us today through the ITER tour, which is the last event of our session today. So Kirsten, thank you for being here, and go ahead.
Thanks very much. Thanks very much. It's really great. I mean, to see all this interest, and what I really liked, I joined the meeting a little earlier and followed Clotilde's presentation. And what I really liked seeing is how the previous visitors here and the previous participants in your initiative have actually used this input and turned it into teaching material for students. That was really cool to see. I saw a lot of deuterium particles. I saw a lot of tritium particles in a moment ago. So that was really quite nice. I'm going to start presentation. What is this here? Share. That's a bit weird. Okay. Share. Okay. You should see a black screen.
Yes, we do see a black screen.
And it should start now. And I see nothing.
Yeah, neither do us.
Here it is.
There it is.
So, I'm going to run it again because we're almost halfway through. We are talking about fusion. And if you look up in the night sky, you see a lot of stars up there in the daytime. Of course, you see the biggest one of all, our sun. And here it comes again. That's what was actually supposed to start. And all of what you see there is fusion. And of course, we want to bring that down to earth. And I hope you will all come to ITER to see what we're doing about it. For the next 45 minutes, I will show you what we're doing here. But first of all, I should maybe introduce myself. Daria has done that. My name is Kirsten Haupt. I'm from Germany. I'm working in communication here at ITER since 7 years now, and I'm in charge of the visit program here and a few other things. And I'll lead you through a little presentation of ITER with some tour elements as well. And I will leave you with a number of resources that you already can use now. So without further ado, let's start. You've already been discussing that a lot. I mean, the framing against which we are talking about, searching for a new and clean source of energy. That's our current energy dilemma that we are in. What we are seeing is that there will be an increasing consumption of energy. In fact, the International Energy Agency predicts that in the next 3 decades, our demand for energy is going to double. So in 3 decades, it's going to double. And that includes everything, electricity, whatever else. I mean, what we need for our lives, that's quite a lot. And that against the background of wanting to phase out fossil fuels. So it's quite a demand. Decarbonization of our societies is not an easy task, and we are very happy that we have gone quite a far way already with renewables. In some countries there is a big use already of renewables, but as we all know, they cannot pick up all the heavy demands. We need more alternative sources of energy to cover that. In one option in some countries is nuclear fission. I always call this the conventional nuclear energy coming from Germany. Of course, we are no longer using it. Last year, we closed our last 3 fission plants in April. But in other countries, it's still a viable option. But as you know, there are concerns about it, safety concerns, but also concerns about waste management. So not all countries consider that as an option. I also noted here as one of the issues that we need to look at CO2 capture. That is one thing where a lot of scientists are looking into to extract CO2 from the environment, from the air, from water, from underground. That is something that we will have to look at in order to mitigate the effects of climate change. And that is very, very energy intense. So we are really looking for a clean and sustainable and abundant source of energy. Now, if we are looking at the sources of energy that we are using today, if you look at each and every single one of them, they all trace themselves back to the stars. Even the nuclear energy, the conventional nuclear energy, everything goes back one way or another to the stars, and in our case to our sun. So why not go to the source? That's what we want to do. We want to bring or create a little sun on Earth. Now, again, a wonderful image here of the sun. A fusion is it's a process that basically runs all our universe. We would not be here if it wasn't for fusion. We have to thank fusion for our very existence. Without fusion, nothing would basically exist. Now, the beauty also is, and for you as teachers, I think this is nice. I know you're very mixed in your backgrounds, and for some of you, this is all very. This might be a little banal, but fusion is a wonderful illustration of that famous Einstein formula. And I give you some more details for those who don't know them in a moment later. So yeah, the E equals mc squared is a wonderful, fusion is a wonderful illustration of that. When we bring fusion on Earth, we do that, we bring it into, that's what we do at ITER, we bring it into a tokamak. This is not the only technology that exists. I mean, there are other technologies. You might have heard of laser inertial fusion. We are doing magnetic confinement fusion that happens in a tokamak like that. What we do there is we do this. We are bringing together two different isotopes of hydrogen. What you see here is a deuterium. On the left, the deuterium. Now they are twirling. So the 2-particle one is deuterium. The 3-particle one is tritium. The isotopes of hydrogen, when they fuse, the 5 particles, they create helium. To some of you, this might also be known as alpha radiation. And you can see that the reaction is so fast and the neutron is so fast, you don't even see it anymore in the resulting image here. Now, I always say that most of the energy lies in the neutron. It has so much energy that when it gets off from this reaction, it reaches the moon in 8 seconds. And that is the energy we want to harvest. But in the alpha radiation, what you see here, the helium, there's also some energy, and we want to keep that as well inside the machine that we are building here. Now, there's a lot more information on how all of that works. Let me just tell you why we are so keen, before I go into some more details, why we are so keen on making fusion work, making the case for fusion. First of all, it's clean. There's no CO2 emission coming from fusion. It's the fuels are abundantly available. You remember the 2 particles you just saw. So the deuterium particle, that's abundantly available in water. I'm not sure whether you're aware, but 1 in 6,000 atoms in the sea is actually deuterium. It's not ordinary water, it's deuterium. So deuterium meaning it has not only a proton in the nucleus, but also a neutron, right? Tritium, on the other hand, is a little bit trickier. Tritium is not a naturally occurring element. This isotope of hydrogen actually is being created in a particular technology of the conventional fission technology. In particular, in North America, it's a side product of the so-called CANDU reactor. But what we are going to do at ITER, we are going to develop the process of tritium breeding from lithium, and we will create this way our own fuel. So this is one of the tasks that we have at ITER. Fusion is safe. There is no great amounts of radioactivity. There is some, like the tritium I just mentioned. Tritium is radioactive, but it has a half-life of 12.5 years, 12.3 years. So that's not very much. If I go back to the container, can you see my cursor? Can you see it? Yeah. The elements here on the wall of the container, we are calling them blanket modules or first wall modules. So the neutrons will hit these first wall modules and they will also activate, they become radioactive and they will have to be replaced. And that will take a little longer. That will take about 100 years, which of course for a human lifetime is a long time unless we are sort of extending our lifetime progressively, but it's a bit longer to consider. But still, in comparison with fission technology, it's very little time and easily manageable in engineering and technology terms. Now, when we start running the machine here, we will demonstrate that fusion actually works. What I'm trying to say here with that is we are not building a power plant here. We are actually an experiment. So we are producing hot water from the fusion reaction. But we are not producing electricity, so we are not feeding anything back into the grid. That is just not very feasible, because as an experiment, you just cannot really predict how much energy produce. It's just not very economical to do that. What we also need to do is we need to bring fusion to an industrial level. That's very important. To do that, we need to, I point out to you this achievement, this level of Q equals 10. What we do here at ITER, we are putting in 50 megawatt of heating power to run the machine, and we want to have 500 megawatt out. That's the idea that we have. So a gain ratio of 10. And that is the gain ratio at the level of the container itself, at the level of the fusion reaction. So this is not 500 megawatt electric, it's 500 megawatt thermal. That's a big difference, because that's really at the level of the fusion reaction, because as you maybe all know, we have a lot of losses in the transition of energy from the thermal to the electric, and then also into the net and the distribution to the consumers. We are actually losing up to, or more even than 2/3. So the Q times 10, so the 10-fold gain of thermal energy in the fusion reactions is necessary to bring this actually to an industrial level, because at that point we will create sufficient helium. You remember the helium from the reaction, to keep heating the inside of the machine, the plasma in which everything takes place. I have run through things a little bit fast maybe for you, but if you have any technical questions, I'm happy to answer them. And I'm also happy to send you material. I'll do that at the end of things, so that you see a little bit where I'm going with things. ITER is a very interesting project in a way. It's conceived. We have 7 members. You see them listed there. It's China, the European Union, India, Japan, Korea, Russia, and the United States. I think Clotilde already mentioned what that means, that we represent half of the world population and about 85% of the world's GDP. So it's quite an economic might behind this project. Now, something that is very special about it is what you see on the right-hand side, the contribution in kind. Normally with international organizations, member states pay into the big pot from which the organization finances their activities to implement their mandate. Now at ITER, that's different. Only 10%, 10 to 20% are being paid like that. The rest is delivered in kind. That means that all the parts of the machine are being manufactured by the countries you see on the screen, whose flags you see on the screen. And that is pretty unique. Europe, for instance, takes the lion's share with about 45% of the contributions. And you will hear me mentioning a few countries along the way. All the other non-EU members of the project contribute about 9% of the project each. So all the big components that you're about to see in a moment are coming from one of those 7 members. That's a very unique way of organizing that. And what are the benefits of it? It sounds very complicated, and it is if you think about integration, but there are also enormous benefits of it. I think Clotilde also mentioned benefits from the project itself that has to do with this as well. There is a lot of expertise created in the countries because of that project, but also companies are being created, whole industries are being created, because what we are doing here is all first of a kind. It's never been done before in this way, and also in this size. So the companies that are producing and manufacturing these items that we need often have to be created, or the procedures, the manufacturing procedures have to be created. So there is a lot of knowledge being created and shared among all the members. There are also lots of jobs created, which is always very important. But one thing also that I would like to mention is the sense of ownership that is being created by doing that. So the countries consider this machine as their machine, our machine, which is very important and gives a lot of drive and motivation, of course. Let me run you through some of the main components. What you see here is the vacuum vessel. Inside the vacuum vessel is does the fusion reaction take place. The fusion reaction takes place in what we call a plasma. It's shown here in white, but plasma is actually pink. I will show you that in a moment, how it really looks like. A plasma is the fourth state of matter. I mean, most of you will know that, as you're probably teaching this. After solid, liquid, and gases, when you heat a gas, you create a plasma. As the atoms in the gas disintegrate into their nuclei and electrons, and that's what you call then a plasma. And that takes you back to the charged particles that I had mentioned earlier, the deuterium and tritium nuclei that fuse to create a helium nucleus and a neutron. So all of this takes place inside here. And now the countries come on top, and you know already where I'm telling you. This vacuum vessel consists of 9 sectors. 4 have been manufactured by Korea, 5 are being manufactured by Europe, and we are expecting in November the first one to come from Europe, 3 from Korea already here. Now this is the magnet system. The magnet system is responsible to confine the particles in the plasma. Hence this whole term for the technology, magnetic confinement fusion. You know that the particles are all electrically charged, so you can use magnets to manipulate them. With these 3 different types of magnet systems, you create in the plasma magnetic field lines that keep the particles inside. These magnetic field lines are in a spiral. If that is too much for the physicists among you, we can also explain it in a different way, but it is quite interesting to know this. Let me go through some of the parts. You will all see them in a moment, in real, not just in animation. In the center here, you see our strongest magnet. That's the pulsing heart of ITER when it all starts. That is the central solenoid. You can make out that it's made of 6 components here. These are 6 colloidal field coils. Colloidal field coils are horizontal, round electromagnets. They are quite big. They weigh altogether over 1,000 tons, and the whole thing is about 18 meters high when it's completed. You can make that out here also by that little person there. So you get already a little bit of sense of a scale. The next system then is here in this sort of mustardy color, the vertical or toroidal field coils. There are 18 of those. They are manufactured in, or have been manufactured in Japan and Europe. We have all 18 of these magnets already on site, plus 1 spare. And then a third big system is the poloidal field coils. Again, you remember circular magnets. There are 6 of them here. You see them in burgundy red. They are cut open so that we can have a peek inside the machine. The top and the bottom one are the smallest ones. Well, when I say smallest ones for ITER, they're between 8 and 10 meters across. The next one up is 17 meters. The next one up, those 2 are 24 meters. They belong to the biggest magnets ever manufactured. And you can imagine that they are so big, they cannot be put on the road. They cannot be transported. They actually have to be manufactured here on site, and they have been manufactured here on site. Again, we have all 6 of these magnets already here. 2 of these magnets are already inside the future machine. And if you were to come to visit ITER, you would see them. You have to come very soon now because we are restarting the assembly process. I come back to that. And the more we go on with things, the less you can actually see. The last big item that I would like to show you is the cryostat. Look at the little figure down here. You get again a sense of scale of how big everything is. You see some of the figures here. This thing is 30 meters across, 30 meters high. Now, if you don't know what a cryostat is, it's essentially a big thermos flask. So it's taking care of the temperatures inside and the vacuum. I've not actually mentioned to you the temperatures. That's actually really impressive. In order to create fusion, we need to have a very high temperature, 10 times the temperature of the sun. The temperature in the sun is 10 million degrees in the core of the sun, not on the surface, in the core of the sun. 15 million degrees, sorry, 15 million degrees. We need to go up 10 times, 150 million centigrade. This is a figure that is really hard to imagine. Already 50 million is hard to imagine. And it's hard to imagine that we're actually able to create that. Now, what you have to think of is that it's not the whole plasma is 150 million centigrades, but the particles in the plasma are so energetic. Remember when I told you that the neutron is very fast? It can reach the moon in 8 seconds. That's the energy that's in there. So that is quite amazing. Now, for the magnets that I showed you a moment ago, for these magnets to be so strong to confine these particles inside the plasma, they need to be super cooled. They need to be cooled down to 4 Kelvin. Again, that's a figure that is really hard to imagine. Yes, of course, theoretically, we all know the figures, but you have to imagine that in the distance of a meter or 2, you have a temperature gradient of, from the center here, of 150 million centigrade hot particles to this magnet around here, where the conductors on the inside run at a temperature of 4 Kelvin. So what you basically have is you're going from the center of the sun to the outer reaches of the solar system within a short distance of 1 or 2 meters or even less, depending on which part you look at. So that is really quite amazing. And what that also does, just to look at the figures, it gives you an idea of the challenges for this technology. It's very, very hard to actually do all this. I will not go on to this one. I mean, suffice to say that as I finish with the challenges, that it is really, really hard to actually do this. Just one word on the comparison with fission and fusion, because there's always that issue of the safety that I had mentioned before. With fusion, you do not have the danger of a chain reaction because it's a completely different physical process. What's really difficult with fusion, it's written here in yellow on that slide, is actually to keep the plasma hot enough for fusion to take place. That is very, very hard. You see up top here, we have various different methods to heat the plasma. But what is really important is that we get to this Q equals 10, because we then have the internal heating, we have the self-heating with the helium that I had mentioned earlier. And only through that can we bring this technology to an industrial level. That is really what is difficult. Now, we are not, of course, the first ones to have tried that. Some of you might know about this project. This is JET. By the way, that white line is sort of a funny design feature. So that's not in the machine itself. And he's not walking on that line either. It's this where you're looking into the machine, into the tokamak at JET. The tokamak at JET is 10 times smaller than at ITER, so the space of it. So this is 80 cubic meters at 80 cubic meters for the plasma. For ITER, it will be 800 over 800. So, and JET is quite amazing because they have run a lot of experiments since the late 90s, and they have established a number of records when it comes to fusion. They have in the late 90s had a first record of running fusion, and that shows you the challenge again. In the late 90s, they had fusion with a 70% output based on a 100% input. So there was not even any there was no energy gain at all. So that tells you also how difficult things are. Now, go 25 years later, last year and 2.5 years ago, they ran experiments on the sustainability of the reaction, meaning how long can you run the fusion reaction on a certain level. And yeah, the figures are, you will understand. I mean, we are talking about nuclear physics, and seconds in nuclear physics are almost an eternity. Have a look at this. So what you saw there was the fusion reaction. I have to stop because I hear the sound too much. The fusion reaction of 23 in autumn. And what they managed to produce there was 69 megajoules of heat. And they already have given a comparison so that you can actually see how much that is. That's the energy release needed to burn 2 kilograms of coal. So that shows you that we have a long way to go yet. But it's the longest fusion pulse that has been created. So that is really quite remarkable. And they cannot get any further because of the size. At JET, the size of the container is not big enough to have a sufficient a number of fusion reactions to actually get a higher gain ratio. That we hope to achieve at ITER. So that's why ITER is so large, because with the space in ITER, with the 840 cubic meters of plasma, we hope to have a sufficient number of fusion reactions to actually create a burning plasma, that is to create sufficient helium to keep heating from the inside, keep heating the plasma from the inside. So we'll see about that. Let me show you now a little bit, enough physics now. Let me show you where we are. You see a comparison, a 10-year distance between the two pictures here. On the left, you see when everything started with the construction in the wonderful south of France in the Provence. On the right-hand side, that was taken a picture with a drone a year ago. And you see the difference and the progress. And next you see a video that takes you a little bit over the worksite. I will point out a few buildings to you so that you know what you're seeing. So this is the main building here in the back. On the left is where the reactor is going to be built in. This is where the assembly hall is. In the front of us here, we have the power supply buildings for the magnets. Here we have the building, the cryo plant that creates the 4 Kelvin helium that cools the magnets, and so forth. So there is too much to really show you. I give you a tool at the end where you can have a look at this yourselves and prepare, use this material for your lectures. Now, this is one of my absolute favorite images. What you see here is the base section of the cryostat. You remember the thermos that encapsulates the entire machine. This was put in, I left the date in May 2020 because that was at the height of COVID. We were super reduced with staff on site. I mean, I myself was working at home. Even the workers, there were a lot less workers on site, and they still managed to do this. I show you a video clip here. There you go. This piece is 30 meters across. You always see some people woozling around here on the floor. Of course, it's sped up a bit, this video. 30 meters across, 8 meters high, and a weight of 1,250 tons. That was the first thing that we inserted in the tokamak. You saw the timeline here. The insertion, just the 30 meters down, took 24 hours. So if you had stood somewhere here, like some of our colleagues here, you see some of our colleagues monitoring the operation, you probably would not have even noticed the movement in parts because it was so very slow. And now I tell you one more information that shows you how challenging that is in engineering terms. This piece, 1,250 tons, 30 meters across, 8 meters high, was inserted there at a tolerance, at an operational tolerance of 3 millimeters, and nothing happened, all went well. I think that is an amazing achievement, what my colleagues have done there. Now, here's our little magnet That one has been manufactured under the responsibility of Europe. That has been made in China. The reason for that is that Europe had to basically manufacture two magnets at the same time, more or less, and that didn't work in terms of space in the workshop, and so that was outsourced to China. But it's the heaviest magnet. This single magnet there weighs 400 tons alone. Next is the first one that was actually manufactured here on site, 17 meters across, an electromagnet, poloidal field coil, as we call it, a circular horizontal magnet. And I'm showing you next a video clip of its insertion. That's just a photo, but now you get to see a video clip of that too. Yeah, you saw how they do that just with that little joystick kind of thing. I checked with these guys that do that, whether they're gamers, and of course they are all gamers. They all play computer games, and they have their dream job working here at ITER as a crane operator. So we are now in the assembly hall. You saw some pictures earlier with Clotilde. There you see it comes up, of course, sped up, 17 meters across. Now wait until the 24 meter is going to go in. Yeah. So this one was about 360 tons. All right, next one. This is, you remember the 18 vertical magnets, that's a toroidal field coil. It is standing, what you see here, in a tool that's called the upending tool, because everything is so heavy. It comes in horizontally into the assembly hall, and it needs to be supported. Otherwise, like a magnet like that, if that was not put against a support like this, it would bend during the lifting. If you just hooked it up at the top, at the bottom, and would lift it, it would bend under its own weight. So it has to be supported with this tool. So next you see how this has been put into the big, one of the big assembly tools in the assembly hall. So here you see the upending tool. You see it is being put up, moved across the entire assembly hall into the assembly tool. This is the assembly tool. Here's the vacuum vessel sector. And now it's been put down there. And later this will be put around on the outside of this vacuum vessel sector. Incidentally, I was actually there when that was done. I was not filming, it wasn't up to me, but I was taking pictures. And I was waiting for the entire day until they actually got going. And I was running around in the entire hall to get good shots. So if you see any photos of this operation, that were mine. Next one. The central magnet, the central solenoid, you saw that earlier. This video has been made. It's part of our last John video from last year. So you only see two parts of the, I'm running it again. You see two of the parts, and they're not even fully connected yet. You see a gap here, right? In the image that I show you that has been taken earlier this year, you see they have been aligned. You see that here, they are already connected. And here's the third one coming. If you were to come visiting now, you would actually see a tower of 4 modules already. So there are 4 items, 4 components stacked on top of each other. And now the vacuum vessel in which everything is taking place. So this is the first one that has arrived here on site. That was in 2021. And here you have a video on how this has been put into one of the assembly tools. Again, notice that everything is being done from the top into the assembly tool itself, but also later for the tokamak, everything goes in from the top. So we have some major cranes in the assembly hall. Each of them has a capacity of 750 tons. They're of course being used together for these kind of operations. I mean, this one sector of the vacuum vessel weighs 440 tons. But if you equip it with the magnets, if you equip it with thermal shields, it weighs close to 1,400, and you really need both cranes. Okay, so this is what you see here. This is the first module that we put into the tokamak, so where the machine is being put together. At the moment, you can still look into it. We still have a possibility to look into it. You can just see here, I think that is one of the openings that we have prepared. We've put in plexiglass in 2 of these openings so that visitors can have a look in. So if you're coming, you can actually have a look inside. let me just show you the components. This is the vacuum vessel sector here. The thin line here is the thermal shield. As you can imagine, with the temperatures that I had mentioned earlier, 150 million centigrades inside here, 4 Kelvin here, or minus 269 degrees here, you need good thermal shielding. That's in between here. So that's a whole module. Unfortunately, I'm telling you about some issues we've encountered recently. Unfortunately, we had to take it out again because we had two problems. We had an issue with deviations in the geometrical shape of these lines that you see here. They are called the bevel joint regions. These are the areas where the individual sectors of the vacuum vessel will be welded together. And they were not according to design and had to be repaired. We thought we could do it inside the tokamak pit when we weld the sectors together, but then a new problem came up with the thermal shields. What you see here is a thermal shield, and you see those pipes on the surface of the thermal shield. There is helium running through them, and we discovered cracks in the pipes. The reason for that is the beautiful surface you see here. These thermal shields had been covered in silver. That silver required a special cleaning procedure. And unfortunately, there was a chloride in the cleaning liquid. And over time, we saw this only a year and a half after these thermal sheets were delivered. We saw discolorations on the surface, and we discovered cracking. Now, this cracking, we could not even measure that. We had to send this to CERN. The image you see there is courtesy of CERN. They have the instruments to measure these kind of things and provide the pictures, the images. Now, this crack is incredibly small. You see this down below the unit. But we have a nice image for that. If you read our article, some of you might have read that already. If you were to fill a party balloon with helium, right, to create these Mickey Mouse voices from a crack like that, with helium, from that pipe, from a cracked pipe like that, it would take you 50 years, 50 years. This is how small these cracks are. But as we are talking about vacuums at a very high order inside these spaces, and losing the helium, we would lose the cooling function. Everything would just go downhill from there. It would just not work. So it is good in a way. It is good that we discovered these issues on time. There are lots of discussions of that. We had to review our baseline for the project. It's been presented this June to our governing body, and in November we expect the final verdict on that. To go forward with this. We have picked up everything. We are now at this stage, we have restarted the assembly. So what you see here, you have a peek into the assembly hall. This is one of the assembly tools. The second one is here in the back. You see here a vacuum vessel sector. And what you see here, sort of yellowish due to some foil, is a repaired thermal shield. So we are starting to assemble the vacuum vessel modules again and continue with the assembly of the machine. That brings me to the end of my presentation. Of course, we are hopeful that things will go forward. We want to have fusion as a part of our energy mix, in particular to provide baseload energy, because that's what's really important. And we want to do that for the young generations right in the future. If you allow me, do I have a few minutes? Yes, I do.
Yes, you do.
I could share something else again. I just want to take you to our website. You might be familiar with that. So if you want to prepare something, or first inform yourself maybe of all the of how it looks like. If you cannot manage to come here, if you want to see things first, what you can actually see here at ITER, go to our homepage. I have to warn you, it's going to change very soon. We have worked on a new website, but this function here will be there again. You need to find it on the new website. I will send the new link maybe to Dario, and you can share it then, because I think it's going to happen this coming weekend that we go into our new website. So, but these features will all be there. All the features that I show you will be there. And Dario, I will send you the links to them. Maybe that's a good idea. Yeah. So that you can share that. So this is our virtual tour. I use that normally for virtual presentations, but then I have a lot more time. So I mean, I usually have like 1.5 to 2 hours, and then I do this. So you go here. This is the last one. Next week, I go on site with our drone pilot to produce the next one. So you will also be able, as of end of October, early November, see the next one. And you come here, and just to give you a first taste, you can do this, right? You can really look around and see everything. Wonderful Provence, right? What I would suggest to you is that you go full screen. You might need to have these thumbnails to navigate your way around. I don't need them anymore, but you see here what you have aerial views. You have, let me just show the magnetic power conversion building. So that is the power supply for the magnets. This is the building, just to show you where we are. This is the building where the magnets were manufactured. We are now using it for other issues. We will update you on that. There are some storage places for our magnets. You see, they are still there. Heat rejection system, that's one of my favorites. That's really cool. We are producing hot water and steam, right? And we need to get rid of it as we are not producing any electricity. So that's pretty cool. Let me take you into the assembly hall. That's what it looks like from the outside, right? You see that it's all very reflective. That's a very interesting feature that under French law, we are in France, under French law, any industrial installation has to involve the local population when they develop the first designs, I guess. There is a term for that I learned last year. It's called social licensing. So, I mean, it goes under social licensing. So people could say how they would like the installation to look like. And people said they wanted to blend into the landscape. I think this is perfect. That image just shows how it works. It's perfect. Let me take you inside. So here you saw the images before, right? The two assembly tools, various items here. You see here a sector of the vacuum vessel. You see here the station for the central solenoid assembly. If you move in here, over there is the tokamak. And let me take you up top. Where are they? Here they are. This is one of the big cranes. You see here the number, 750 tons. As I said, the other one is here in the back. So this is one of the resources I wanted to show you. And then I made some notes because you talked about education. Let me show you this here in the carpet, education. Go in there. You find a lot of resources here, in particular here in Fused. You find a lot here, materials, you find all sorts of things. And that's not just by ITER, that's from all over the world. Okay, so a lot of stuff that you can do, that you can use. One thing I would like to point out to you particularly, I'm not sure whether I can find that quickly now. Materials. Let me go into our website and you see immediately where you can find it. Videos, go into videos. And then you go into the categories machine assembly. And then you go into this story here. Stop. So there is a video here on how you can assemble your own tokamak. The related story, I'm not sure, news videos. Let me see whether that's in the story. No, I will have to send that to you. We've had a story in 2020 when we started assembly at ITER, where we provided the source files for 3D printing of this very tokamak that you see there. Dario, you might remember Tamas from Soft, yeah.
Yes.
They created that. Okay, they did that. A Hungarian colleague. So we make that available, so you can also source that online. And I think that brings me to the end very punctually. Cool. Very little time for question. I'm really sorry for that, but yes, so I stopped sharing.
Kirsten, thank you very much for, I would say, this outstanding presentation. You know, I've been lucky enough to visit ITER often, but I would have to say that your presentation is the second best thing to compare to being an ITER present. So thank you very much. Yes.
Thank you. That's really nice.
The guidance and also all the audiovisual material along with your description. That's amazing. Thank you really so much.
You're welcome.
I think that's a nice presentation. We have a couple of questions from the audience. So there is Stefan wants to know if it would be possible to use your presentation for his lesson, because I think he would be really suitable for educational purposes. So
let me just have a look in there that everything is okay in terms of like legal issues like copyrights and all of that. And once I'm done with that, but I think it should be, because I often share my presentation, the normal presentation I give, okay, which is a lot more extensive and gives you a lot more detail. I can send you that anyway. Gives you a lot more details on how Fusion actually functions. Yes, I can share that. I'll just have to look through this particular presentation to make sure there's nothing in there that I cannot share. Okay, and normally you can use it in your classes. For that reason, because I'm not sure that everything is okay legally. I would not like it to be published anywhere on YouTube or something, but you can use it as a resource. Yes, sure, for sure.
okay, thank you for that.
Yeah.
There is another question on what are the environmental and social implications of the development of Fusion?
Again?
What are the environmental and social implications of the development of Fusion?
There's always something. Yeah, environmental, there's always something. Nothing that we do doesn't leave any trace. I mean, sourcing raw materials, and there is a lot here. I mean, it has the same issues like any other industry. Like just think about the creation of tritium. It needs lithium. I mean, when you see documentaries on how lithium is mined, I mean, that's horrible. But that's where we are. I mean, if we do anything, we have impacts. I mean, I don't want to excuse that at all. I'm worried about that too. But yeah, there are some impacts. There is one interesting note. I told you about the safety. That is, I mean, that's also an environmental hazard, if you like, but it is very limited in some ways. As I said, I mean, it takes about 100 years until the electricity has dissipated from the used parts, and then they can be used entirely again. So there is no radiation beyond the machine. There is very little radioactive material there. So in that sense, the environmental risks are very low. Another thing is that the footprint of fusion power plants is very small in comparison to other power plants. So that's in environmental sense, the land use is a positive factor. On the social implications, where are you getting with that question? I need a bit of a pointer here.
I'm not really sure. So maybe if we get another, because that's the only question. Maybe if we get another comment, then we can.
No, it's interesting. I like it because you know what I can talk about it. I mean, I'm going often to conferences, and I had mentioned the social licensing. The social licensing, I only mentioned this, the inclusion of the local population in defining on what an industrial installation like this looks like. But there are a lot more implications. Social licensing also includes like, how does it look like for people in the area to have jobs in a fusion power plant, right? I mean, what is that with the footprint? What is that with the water use and all of that? There are lots of issues, lots of questions. I cannot answer them all. One social implication, or rather almost political implication. I had the short version, so I didn't see the slide about the history of ITER. ITER comes from the end of the Cold War, believe it or not. I mean, that is quite incredible. So Reagan and Gorbachev, during their disarmament talks in Geneva in 1985, agreed to include the development of fusion into their disarmament agreement. So that's what all of this is based on. That was 1985, think about it, at the end of the Cold War. In the agreement, it says that the countries that are now part of the ITER project commit to develop fusion for the benefit of all mankind. Now, all mankind is more than the members of ITER. What is going to happen with all the other countries? What is happening with the global south? I am always sort of a little bit the devil's advocate at conferences, and I'm asking that question because we don't know that yet at the moment how that's going to work. At the moment, we are too entangled in the science, but I think we need to look at this, how we are sharing the knowledge, how we are sharing the expertise, how we are sharing the technology, how we are enabling access to raw materials to all those outside the member states of VITA who want to do that. We are not the only ones wanting to have fusion energy when it comes about. I mean, all the countries in the world wants to have it. That's a big question as well. I'm not sure whether you were going there with this question, but if you want to give me more details, maybe I can answer your question then.
Okay, thank you for this. There is let's talk about ITER and visiting ITER itself, because there is the interest of teachers going to ITER. I know you are involved in the ITER visits as well, but also not only for teachers, but even from our dear colleagues from CIEMAT, who had also a very nice presentation earlier today. They would also be interested in going to ITER. So how does it
work? Let me share something. I'll go back to our website. Okay, where is it? Here. Okay, I can show you straight away. I'm going to close this. How can I get rid of this? Here, you see here up top, visits. Can you see it? Yeah. So you go in there, you see group visits, individual visits, you go into group visits, and you have a calendar here, and you can book your slot. If that doesn't work, you just write to me. Okay, so you have a slot here, you go in there, go on a slot, you answer all these questions, and then you just continue, and you can organize your visit. Now, just one word of caution: don't be perturbed by that. If you want to have a visit, like you have your physicists and engineers coming to visit, this is more for the general public. If you let us know that this is for engineers or for plasma physicists or whatever, for experts, then we adjust that. So don't be perturbed by this short time frame. I mean, this is a normal visit for the general public. We give them a presentation of 45 to 50 minutes, then take them on site. Most of them we take into the assembly hall. We don't take them into the tokamak. But for expert visits, we also take people into the tokamak. All of that is, of course, with a caveat you have to understand of operational restrictions. There's always that. We never know what happens. I mean, I'm going to fly the drone next week, and I have green light for everything, but God knows what's going to happen. I mean, they want to move some toroidal field coils into the assembly hall, and I might be told one day, no, sorry, you can't come in. So this can happen anytime. But believe me, we are doing our best to accommodate you. Okay?
Okay, very good. I think I will take your time for probably just one or two more questions, and then
Go
I'll let you
go
go
ahead.
if that's
I
okay.
can answer them, I'm happy to. Yeah.
Thank you very much. So this is there's a question saying from Juan: what industries are profitable around the fusion energy business? What areas of physics or engineering should benefit about this research?
Oh, all of them. Seriously, I mean, if it's about engineering, you shouldn't just be a nuclear engineer. We need mechanical engineers, we need civil engineers, we need all sorts of engineers. We need, are you asking in terms of getting a job at ITER or at a fusion power plant? If that is the case, you need literally everything. I mean, you need the physicists, but more and more you need the scientists of all couleur. Seriously, we have engineers specialized on water technologies, because we have cooling water. You need everything, but we also need to run a plant like that. You need IT specialists. You need administrators. I mean, it sounds a little bit banal, but yeah, of course, you need finance experts. You need all sorts of people. When you build a plant, you have a lot of procurement. You need these people. Yeah, so there is a whole range. You need people like me. You need communicators. You should, when you do that, involve communicators from the start, so that there is always someone who connects to the outside of your project to share and to share the information. So you need all sorts. I hope that answers your question.
I think that's very good. And then, thank you. Then we go with the last question, a little bit technical regarding coolant. So I'm cooling the system. So the question is from Babka: how much water or any other cooling solution would be needed for a hypothetical 1 gigawatt electrical output fusion a
I
power
cannot
plant.
give you. I
Yeah.
cannot give you the amount. I cannot give you the amount. Suffice to say that we have two different kinds of cooling agents. We have helium, and it goes. I mean, the helium in all the magnets is about 1,000. What, 1,000 liters? No, must be more than that. It's huge. It's a big number. I have so many figures in my head. This one I don't. But I don't know. Wait a minute. Maybe I can show you something that gives you an idea how much there is. Let me see. Okay. I'll take you into the tour. Perfect. You know, I can show you something.
That's very good too.
Yeah. No, this is what, I mean, yeah, I don't know the figure, really, honest to God, I don't know. Cryo plant here. All right. You see the tanks here? Yeah, they are filled with gaseous helium. That's how much we need for the magnets, and they're already full with gaseous helium. They need to be cooled down, right? So this much helium we need for the magnet. And besides, this helium has nothing to do with the helium that's created in the fusion reaction. They don't get together at all. All right. I mean, that's completely separate. The other coolant that we are using is water, actually. We are using a lot of water. Let me go to the cooling plant. Where is it? Heat rejection system. Here it is. So what you have here is our cooling system. We are using water to cool, to take the energy out of the vacuum vessel. So the heat that is being created by the neutrons impacting on the inside wall of the vacuum vessel, you have a transfer of kinetic energy into heat. That heat is picked up by water in the pipes running in the wall of the vacuum vessel. The water is under pressure. It's 140 degrees hot. I mean, pressurized water, you can heat higher. So when it runs at a very fast flow rate of 6 meters a second and takes the water out, you see all the pipe systems down there. There are various systems in there. We have two basins. We have a hot basin under this area where all the cooling water from the plant gets to. It's the cooling water from the tokamak, but also the cooling water from all the plant systems, because we have cooling in other plant systems as well. That's about 10,000 cubic meters in here. Then you have here a system of heat exchangers, and here you have the cooling tower. So the water then gets divided up. A part of the water goes back through the heat exchangers back into the system to cool again. The other part goes out, is enriched with other water, because when we cool it down, we are basically evaporating water. So the mineral content increases. We have to correct that. We also have to check it for contaminants, and then we put it out into the environment again. We are taking all our water from the canal system here, the irrigation system in the south of France, the Canal de Provence, and we are putting it into the river Durance, but not before we have checked for the quality. Unfortunately, I can't tell you how much water it is. I would say it's quite a lot.
Yeah, I think
that's all I can say. I'm sorry.
No, I understand. Also because going from, like you mentioned before, going from thermal to electrical, that's all different things. So yeah,
it was complete when I started working here, and I'm not an engineer, I'm not a physicist. I mean, when I started working here, this was all news to me, and I was actually quite shocked, to be honest, that there is such a loss in transition from megawatt thermal to megawatt electric, and that's with every energy source we have. Yeah, so I'm wondering whether we should put some energy in research and stuff in that to reduce it, but I don't know whether that's so easy. It's easier said than done, obviously.
Okay, thank you very much. I
Dario.
was thinking about closing this session, but I have only one last question because somebody raised their hand. So if you don't mind,
problem at
one
all.
last question and we're closed.
Yes.
Thank you. Thank you so much for your time. I'm gonna open the mic here to the person who raised the hand.
Herr oder Frau Leuenberger.
Leuenberger. Yes.
I think the mic is still off. I think you're still muted.
Yeah, but should be able to.
Or write
be able to be
question.
open to. Okay.
Well, Right, whatever. Yeah,
All
okay.
right.
So I hope, I mean, thank you very much for the invitation. Again, I have to say that I was quite impressed by what I saw earlier, by what has already been done. I think it's a very good thing. And there was a note that Clotilde said that we really need future generations of engineers of all couleurs to work at this. And I can, Dario, you were at SOFT as well. I don't know whether you saw the presentation of Gianfranco Federici of Eurofusion. That was one of his closing arguments. We need to invest in education. We need future generations of engineers, of administrators, of physicists to work in what is coming in the future decades. So this is really, so you have a very important mission there. And I'm really happy that you have all that you're all participating in this. And I wish you really, really good luck in bringing this into your classrooms.
Thank you very much for those words, Kirsten, and also thank you to you, because you at ITER and also the ITER communication team is doing a great effort towards education and outreach with the public, the teachers, and everybody around. So I wish you the best.
Maybe I see one or the other in summer, because I'm used to also doing some of the tours for this initiative.
Yes, that's really good. Let's see what Clotilde and the commission tell us about the new visits, and then hopefully, yes, we will be seeing each other there.
Exactly.
Kirsten, thank you very much for attending the event, and yeah, good luck with the rest of ITER activities that always going on.
All right, you have to follow. Yeah, for all of you, if you want to really stay closer to what happens at ITER, maybe I should just go in here again, just show you quickly, since I am online here and I'm still sharing. I just take the liberty. You go into ITER Newsline. It will look a little bit different in a couple of weeks, maybe already in a week. FuseNet student event, you see, I mean, we're taking note of everything. Yes. You have here the subscribe button. You can subscribe to this very newsletter and you will always be updated. So that's a good thing to do. Yeah.
Yes, definitely.
All right.
All right. Thank you so much, Kirsten.
Okay.
And then with Kirsten's intervention, I think we're closing the program for the day. So I would like to thank all of you for staying with us during this event. I hope it was useful for you. I hope you found it valuable and entertaining. And our idea is that you still aim to promote fusion knowledge in your classroom with your students, having enough knowledge from what you've seen here, and also from the materials that you have available to use, and to join us in this global effort towards achieving fusion energy, but also towards educating the future generations in fusion, because at the end, you know that it's been mentioned that this is a process that involves the new generations, because at the end they will be the ones moving forward with fusion, and we want to have them involved from the early age, because this is a legacy that we're leaving to them, and we're looking forward to having the participation of the next generations into this global effort. So thank you, and you are the most important part, is that you are the key to reaching these generations. So we believe that the work of the teachers is crucial and fundamental in being able to transmit this knowledge and this urge to work into fusion. So we hope that it has been inspiring for you as well as teachers. Thank you very much. We stay in touch. You will receive from us email also with the feedback form from this event, but also all the links that Kirsten will share, and also from the other speakers, from the visits and everything. And we stay in touch. And like I mentioned before with Clotilde, once we know the dates for the commission visits, we will send you an email as well. So thank you very much. Wish you a good start of the weekend, and thank you for being here. See you in the next event.